All right, 312. So there's part A and a part B. We're just going to do them all in one video. So the first one we are talking about is equivalent representations of trig functions. So now what we're going to do is I'm going to give you a bunch of trig functions that are very, very helpful when solving some certain problems, and you're going to see how that comes into play. So the first thing we're going to do is we have our unit circle, right? So we can actually figure this out from our unit circle. Right, let's just go ahead and just say, let's make our 30, 60, 90 triangle right here. This one is x, here's y, and my radius is 1, right, my hypotenuse. Well, when I do right triangles, what's the most common thing for right triangles? Well, it's kind of in our name up here, the Pythagorean theorem. We have a squared plus b squared equals c squared. But now when it comes to a unit circle, right, I can actually replace the x, the a and the b with cosine and sine. And how that would look is I would have cosine squared of x plus sine squared of x equals 1 squared. I'm not going to write the 1 squared because 1 squared is just 1, right? So that is my first and arguably one of the most important trig functions. It's honestly like the parent trig function because you can actually get all the other trig functions just from this one right here. So the first one we're going to do with this Pythagorean identity is we're going to just start off by subtracting cosine to both sides. And we end up with sine squared of x equals 1 minus cosine squared of x. And then if we do the same thing, but instead of subtracting cosine, we subtract sine, we get cosine squared of x equals 1 minus sine squared of x. So right now, at this point in time, these are our most important trig functions. I wonder if I can get it to be a little bit better. It's very skinny, right? Guess not. So, oh, okay, I did fix it. So we have this one, and then this first one right here. So again, if you only remember the first one, you are going to be fine because you can figure out the rest from just this simple manipulation, right? So we have our first one here. It says reciprocal Pythagorean identities. Well, once again, there's our main one, right? Sine squared of x plus cosine of x. Remember, it doesn't matter the order, they're just addition. So the order does not matter when it comes to addition. Well, if I divide everything by sine squared of x, what would happen? This becomes 1 plus, now cosine squared of x over sine of x, that should be familiar because we just did it in 3.11, that's the cotangent. So you would have cotangent squared of x equals, and 1 over sine squared of x is going to be the cosecant squared of x. Okay, now let's say we do the same thing, but on the other side, I'm going to divide by cosine. Well, that one's gone. This is the regular tangent. So tangent squared of x plus 1 equals the secant squared of x. Okay, so now we have 2 more trig functions, and actually I can rewrite both of them so that I get the cotangent squared of x equals, if I subtract 1 to both sides, the cosecant squared of x minus 1. And again, if I subtract by 1, I get that the tangent of squared of x is equal to secant squared of x. So now let's go ahead and use these identities to rewrite each expression in terms of a single trig identity. Okay, so this first one here, well, I'm going to rewrite tangent as sine over cosine. And remember, when they're right next to each other, that's multiplication. So cosines now are going to cancel out, and I'm just left with sine of x. Okay, now the next one, we're actually going to use our properties, right? So 1 minus cosine squared of x, well, if I look right up above here, there it is, sine squared. So sine squared of x over cosine squared of x, well, that's going to be tangent squared of x. And there it is simplified. Now the last one, once again, here's my main Pythagorean identity. Cosine squared of x plus sine squared of x, well, that's going to be 1 over, and then I have here the sine of x, and I'm going to rewrite the secant to be 1 over cosine of x, right? So then if I'm going to now just focus on the denominator here, so that's going to end up being sine of x over cosine of x, and then over that 1, meaning what's going to happen is I'm going to go ahead and have 1 times the reciprocal, which is cosine of x over sine of x, which means that my final simplified version is just the cotangent of x. Okay? Now, here we have some tips. Rewrite in sine and cosine. So if you can get things to be in the sine and the cosines, that's what you want to do, right? Squared trig functions could be Pythagorean identity. As we saw, we had here all the cosine squared, cosine squared, cosine sine squared, all those signs. You should already, when you see them there, the exponents, you should start thinking of identities, okay? And put in terms in one trig function, right? So when you have a problem and you have to solve for a value, you want it all to be in one trig function. That makes it a lot easier to solve. So now here we have some problems. So notice that it says solve the trig equations for 0, so between the domain of 0 and 2 pi. So basically within one circle. Okay, so the first thing I want to do with this first problem is I want to change this secant squared of x so that I can get it to be a tangent, right? And I have an identity for that. If I look back over here, well, let me see. Secant squared of x is equal to tan squared of x plus 1. So 1 equals tangent squared of x plus 1 plus tangent of x. If I can spell it right, tangent of x. And then I'm going to go ahead and subtract 1 to both sides. Well, there's my 1's are gone, leaving me with tangent squared of x plus tangent of x equals 0. Now, I notice, well, both of these have a tangent, so I can go ahead and factor it out. That's my greatest common factor, a tangent of x. And that leaves behind tangent of x plus 1. And now, just like when I do my factorings, I'm looking for when tangent of x equals 0 and when tangent of x plus 1 equals 0. Well, if I subtract 1 to both sides, I'm looking for when tangent of x is equal to -1. So when does tangent equal 0? Well, if I look in my unit circle, which I don't actually have here, but we can figure it out. Tangent of 0 is going to be when my sine is 0. Remember that it's sine over cosine. So in order for this to equal 0, my sine has to be 0. So that's going to happen at pi and 2 pi and 0. So it's going to occur at 0, pi, and 2 pi. And then now I'm looking for when the tangent is -1. So when the tangent is -1, remember that my sine and my cosine have to be equal. So that means I'm looking at pi over 4s, right? So I'm also now looking when my tangent is negative. Well, tangent is negative in quadrant 2 and quadrant 4. So in quadrant 2, I have 3 pi over 4. And I have in quadrant 4, 7 pi over 4. And these 5 answers are your answers. So you have 5 possible values for this trig problem. So now let's go ahead and look at the next one. So we have here another identity, right? This is derived from one of our main ones up here, sine squared of x, or no, cosine squared of x equals 1 minus sine squared of x. So I can just go ahead and rewrite it as cosine squared of x plus cosine squared of x equals 2. Well, if I add these up together, I get 2 cosine squared of x equals 2. Divide by 2, and I'm left with cosine squared of x equals 1. Now remember, I need to get rid of that square. So what's going to happen is I'm going to square root both sides. And remember, that gives me cosine of x is equal to plus or minus 1. So now I have to look at my unit circle and figure out when it's going to be 1. Well, in this example, that's going to be, my cosine is going to be my x's. So when my x's equal 1, that's where my values are going to be. So it's going to be at 0, pi, and 2 pi. Okay, because remember that these points here are 1 comma 0, 1 comma 0, or negative 1 comma 0. So that's my positive version and my negative version. Okay, now we're just going to jump straight into 3.12b. So 3.12b is now more trig identities, but now we're looking at sum and difference identities. So we have first here sine of alpha plus beta. So these are going to be specific equations that we get, which the first one is going to be sine of alpha times the cosine of beta plus sine of beta times the cosine of alpha. Okay, and then very similar, when I'm subtracting, it's going to be sine of alpha times the cosine of beta minus sine of beta times the cosine of alpha. Now, when it comes to the cosines, it's a little bit different. So first of all, rather than sine and cosine, it's going to be cosine alpha times cosine of beta. And then whatever sign is here in the middle, I'm actually going to use the opposite of it. So minus sine of alpha times the sine of beta. And the same thing's going to happen over here. It's going to be the cosine of alpha times the cosine of beta plus sine of alpha times the sine of beta. Now, if you want the explanation on how these equations are derived, please let me know in the comments, or you can tell me in class, and I will gladly share with you the video where it explains how these equations are derived. I'm not going to waste time trying to explain that when there's a video that you can watch that is very helpful. And so I'm just going to go ahead and start with these examples. So I have the sine of pi over 4 plus the 5 pi over 3. Well, that's going to be sine of pi over 4 times the cosine of 5 pi over 3 plus sine of 5 pi over 3 times the cosine of pi over 4. So sine of pi over 4, well, that's square root of 2 over 2. Cosine of 5 pi over 3, that's going to be 1/3. I mean 1/2. Plus the negative square root of 3 over 2 times square root of 2 over 2. right? So when I go ahead and multiply these, I get square root of 2 over 4 plus the negative square root of 6 over 4. So remember, I'm combining what's on the inside, but I can only do that because it's multiplication. Now when I get to my answer is just going to be square root of 2 minus square root of 6 over 4. I cannot combine what's inside of a radical when it is adding or subtracting. However, when it is multiplying, I am able to just multiply the insides. Okay? So now we have the second problem, which the second problem is, I think this one is fine. Yeah, this one is fine. It's going to be, and there's another problem later on that is a lot more work. So here I have the cosine. So the cosine is going to be cosine of 7 pi over 4 times the cosine of 2 pi over 3 plus sine of 7 pi over 4 times the sine of 2 pi over 3. I ran out of space there. So again, cosine 7 pi over 4, well, that's going to be positive square root of 2 over 2. And then the cosine of 2 pi over 3, that's not in the first or fourth quadrant, so it's going to be negative 1/2. And then it's going to be plus negative square root of 2 over 2, because sine is not positive in the fourth quadrant, only in the first and second. And then cosine of 2 pi over 3 is going to be square root of 3 over 2. So now I'm going to go ahead and do the same thing. I'm going to multiply, so I get negative square root of 2 over 4 plus negative square root of 6 over 4, which is going to give me negative square root of 2 minus square root of 6 over 4. And those are my two final answers. So now I have one more example, but I'm going to leave that one to you. So you're actually not going to be solving, you're just going to simplify, right? You can't actually solve this because it's x minus pi over 6. There's no actual radian for that x. So I'm going to let you try that on your own, and then we can work on that together. The next one, we have our double angle identity. So again, I'm not going to go into how you get these. I'm just going to show you what they are. So a double angle identity, when you have sine of 2a, it's going to be 2 sine of alpha times the cosine of alpha. Let's start one up. And then for the cosine 2a, what's going to happen is I'm going to have cosine squared of alpha minus sine squared of alpha. And then what I can actually do is I can actually derive equations from these, because this is that original trig function we did earlier in this video. It is the cosine, oh, but it's minus, so it's a little bit different, but you know, you can adjust it so that it works. And from this equation, what you can do is you can actually also derive 1 minus 2 sine squared of alpha, and you can also get 2 cosine squared of alpha minus 1. I believe you just replace cosine squared and sine squared with the identity. Okay? Now, in solving a problem, we are going to do this one together, and then I will leave you with the other one on your own, and that will be the end of this video. So, first thing I want to do is, well, rewrite sine 2 of x. So that's going to be 2 sine of x cosine x equals cosine of x. So I'm going to start by subtracting cosine of x to both sides. That's going to cancel out and give me 0. And then I'm going to have 2 sine of x cosine x minus cosine of x. Well, now, just like in the previous problem, I have a cosine in both, so I'm going to go ahead and factor that out. That's going to leave me with 2 sine of x minus 1 equals 0. So cosine of x equals 0, and then 2 sine of x minus 1 equals 0. I'm going to add 1 to both sides. Then I'm going to divide by 2, and that's going to be when sine of x is equal to 1/2. So I'm now looking for when cosine of x is 0 and when cosine of, or when sine of x is 1/2. So looking at that, we already kind of did that. The cosine of x to be 0 is going to be happening at pi over 2 and at 3 pi over 2. Okay, and then when sine is 1/2, that's going to happen at pi over 6 and at 5 pi over 6. Remember that you need to include the quadrants that are going to be positive, okay? And then you are going to be able to solve the second one on your own. I'll start you off so that you can get an idea. You first want to move this guy over, so that you have 3 cosine of 2x minus 2, or no, not yet. You don't want to move that over yet. You want to rewrite this so that it is 3, and then you're going to say 2 cosine squared alpha minus 1. You want to use that identity because of the fact that you have it equal to cosine squared of x. You don't want to be adding a whole bunch of different trig functions. You want to keep it as cosine if that's what you have. Okay, and with that, that is the end of 212. All right, so 313 will be coming soon.